In this video, we shall look at a couple of review problems associated with motion of satellites. First, a brief introduction. Assume you have a planet, and there is a satellite orbiting around this planet, say in that direction. The orbital distance of this satellite from the center of the planet is, let's call it r. And its orbital speed is v. Let's assume the mass of the planet is capital M. We shall see how capital M, orbital distance, and orbital speed are related to each other. We know that the centripetal force on this satellite, say whose mass is little m, is given by the mass of the satellite, the square of the orbital speed, over the orbital distance. And this centripetal force that is heading towards the center of the planet is provided by the gravitational attraction from the planet, and that is given by Newton's law of gravitation, capital G, the mass of the planet, the mass of the satellite, over the square of the separation distance. You see, the little m goes away. The r from the left will cancel one of the r's from the right, giving us an expression for the orbital speed, namely as capital G times the mass of the planet divided by the center of the center distance, square root. This is an important equation that we shall use in the review problems in a minute. Problem 1. A satellite around the Earth moves in a circular orbit with orbital speed of 6,500 meters per second. Find the orbital period and the radial acceleration of the satellite in its orbit. So let's assume that is the Earth, and the satellite is at some distance, right there, and that is the orbit, the circular orbit it takes roughly, and the orbital distance is little r. The orbital speed, let's call it v, and we know what v is, 6,500 meters per second. So let's do part A. The orbital period is given by the total distance the satellite travels as it makes one revolution, which is the circumference of that orbit, 2 pi times the radius of that circular orbit, divided by the orbital speed. And from the previous equation, we know that the orbital speed is related to the orbital distance by this equation, which we can use to get the orbital distance as quite simply g, the mass of the Earth, over the square of the orbital speed. So the orbital distance r is given by 6.67 times 10 to the power minus 11. That is the gravitational constant. The mass of the Earth is 5.98 times 10 to the power 24 kg. V is known to be 6,500 meter per second, and don't forget to square that. And this will give you the orbital distance in the unit of meters. And that's going to give you a value of 9,440,615 meters for little r. Now putting this little r in here, we can determine the period. And if you do that, you get t equals 2 pi. The orbital distance is 9,440,615 meters, divided by the orbital speed of 6,500 meters per second in seconds. And that's going to give you 9,126 seconds. Now let's do part B, the radial acceleration. The radial acceleration is heading towards the center, and that is known as the centripetal acceleration of the satellite towards the center of the Earth. That's given by the square of the orbital speed over the orbital distance, both of which we know. So v is 6,500 meters per second, square that, over little r, which you have found before, 9,440,615 meter, and that's going to give you the answer in meter per second squared. And when you calculate, you'll get 4.48 meter per second squared. And that solves the problem. Problem 2. Find the speed and the orbital period of a 250 kg satellite in a circular orbit 650 kilometers above the surface of the Earth. So let's do part A first. So that's the Earth and that's the satellite. And the orbit is like that, let's assume. So the satellite's mass is 250 kg. And the altitude, that means this distance, is 650 km. And of course, we have not included the radius of the Earth just yet. Now, let's assume we are told that the radius of the Earth is 6.37 times 10 to the power 6 meters. So before we find the orbital period, we need to determine the orbital speed v. And that is given by the square root, the universal gravitational constant capital G, times the mass of the Earth, divided by the orbital distance capital R. Now let's assume we are also told the mass of the Earth as 5.98 times 10 to the power 24 kg. So putting everything together, we will get the following for the orbital speed. It's 6.67 times 10 to the power minus 11. The mass is 5.98 times 10 to the power 24 kg over the orbital distance, which is the radius of the Earth plus the altitude. So that is 6.37 times 10 to the power 6 plus 650 kilometers. Converting that into meter, you will get 650,000 meters. And when you do the calculation, you get 7,538 meter per second for the orbital speed. Now, having found the speed, we can determine the orbital period by taking the circumference of the orbit and dividing that by the orbital speed. So you get 2 pi, capital R is the radius of the Earth, which is 6.37 times 10 to the power 6 meters, plus the altitude, which is 650 kilometers, so 650,000 meters that is, divided by the speed which we have just computed, 7,538 meters per second. And that's going to give you the orbital period in seconds, which is 5,851 seconds. So we shall record the answers for part A there. Now let's move on to part B. If the satellite above is losing its mechanical energy at a rate of 1.5 times 10 to the power 5 joules per orbital revolution, find the satellite's altitude, the satellite's speed, and its orbital period at the end of its 1,400 revolution. Assume the satellite's orbit is a circle of gradually diminishing radius throughout the process. Now what that means is the change in energy is the final energy minus the initial energy, and that can be computed. In each orbital revolution, it loses that much energy. So after 1400 revolution, the decrease is just 1400 times 1.5 times 10 to the power 5 joules of energy, which will give us 210 million joules of energy. And this is a reduction in energy, hence the minus sign. But we also know the change in that energy is given by EF minus EI. So EF is just the final potential energy, that is minus G, the product of the two masses, the mass of the satellite and the mass of the Earth respectively, over the final distance of the orbit. Let's call it R sub F. So R sub F is the orbital distance of that orbit, R sub F. So as the satellite makes its transition from the original orbit with radius r sub I to the final orbit with radius r sub f, it loses this much energy. So that is the idea. Now E sub f is given by the potential energy plus the kinetic energy. The kinetic energy is half the mass of the satellite times the square of the orbital speed of the satellite when the satellite is there. So let's call it V sub f squared. To that we have to subtract E sub I. So E sub I likewise is the original potential energy, G, the product of the two masses over R sub I. We know what R sub I is. It is just 650 kilometers plus the radius of the Earth, plus half the mass of the satellite times the initial orbital speed squared. Now we can express V sub f in terms of R sub f using the equation that we have written a few times, square root G, the mass of the Earth, over R sub f. Substituting this in here, we get this term. You see that this added to that will simply give you minus gmm over 2 r sub f. So in this equation we have everything except r sub f, and that can be solved. So let's put everything together. Delta E, which is this, so it's minus 210 times 10 to the power 6 joules, equals minus g, the mass of the satellite is 250, and the mass of the Earth is 5.98 times 10 to the power 24 over 2 times r sub f minus g. Again, the mass of the satellite is 250, the mass of the Earth is 5.98 times 10 to the power 24 over r sub I. R sub I was the radius of the Earth, which is 6.37 times 10 to the power 6, plus the original altitude, which is 650 kilometers, 650,000 meters, that is, plus the original kinetic energy is half times the mass of the satellite, 250, half 250, and the original orbital speed squared, which we have computed in part A, 7,538 meters per second squared. And you see you can get r sub f, which will result in the following value for r sub f, 6,818,736 meters. So in order to get the new satellite's altitude, all you have to do is to take the r sub f minus the radius of the Earth, and that's going to give you 448,736 meters. So that's the answer for part C, or about 449 kilometers. Now we can determine this new orbital speed, or the final orbital speed. It is given by the square root g, the mass of the Earth, over r sub f, which is the final orbital distance. Substituting the numbers for capital G, the mass of the Earth is 5.98 times 10 to the power 24 kg over r sub f. From there, 6,818,736 meters. You get the following for the V sub f, which is 7,648 meters per second. And finally, the orbital period. So the orbital period, capital T, the final orbital period when the satellite is there, is given by 2 pi r sub f, that's the circumference of the orbit, divided by the final orbital speed. Substituting the numbers for r sub f and v sub f in here and here, we get the following: 5,602 seconds, or about 93 minutes. And that solves the problem. Thank you for watching.